So before we get into actual networking, just going to go over a couple of concepts. First of all, abstraction layers. So anyone heard of the term separation of concerns? It's a design principle in programming that's about, and for computer applications and systems and whatnot, the idea is to break down a huge project or problem or whatever into different components, and each one has exactly one responsibility or concern. So you see that in a lot of places in programming. So for example, you will often break down code into a bunch of functions. Each function usually, if you're doing it well, each function will have exactly one thing that it's responsible for. And even if you're not going to reuse it a lot, it's often nice to break things like different responsibilities out into different functions. For example, in C++, translation units, they don't really have much of a specific meaning other than one code file has one translation unit, so it's often nice to be able to break it down logically into this translation unit is responsible for this small aspect of the project, this one's responsible for that one. Same idea with directory storage of projects, you'll organize code into different folders depending on what it's doing, right? So that's pretty core thing in programming. So one fairly common model for separation of concerns is called abstraction layers. So the idea, again, is every layer deals with a specific type of problem. So and generally each layer can only use APIs or whatever you want to call it from layers below it. Sometimes only the one directly below it, not always the case. Large scale example, for example, you have JavaScript running in a web browser doing something, say trying to wait for keyboard input, trying to read input from the keyboard, right? So JavaScript, it's running in the, say in Google Chrome. So it's running in the V8 JavaScript engine, which is the engine used in Chrome. So JS. Then that's interacting with Chrome because Chrome's providing all the APIs that JavaScript can use, right? Chrome is actually running on an operating system probably like Windows or Linux or OS X, so that's using the OS's libraries for waiting for keyboard input, which itself is communicating with the driver, because you could have a USB keyboard, you could have a PS2 keyboard, you could have you could have a Bluetooth keyboard, you could have different things, and now those will have different drivers. And the driver is then actually, I'll say this, so the part of the driver is probably implemented in assembly. So it's directly interacting with CPU's I/O ports, but even that is an abstraction of what's actually going on, because that will often be the same assembly work on different systems, but the actual physical wiring is different and whatnot. So that's another abstraction layer on top of the actual hardware, and we could keep going to a certain point, right? But the idea is that because this is structured in that way, I mean, it looks like it's very complicated, far too complicated than you'd expect for a program to just wait for keyboard input, right? But it then allows, that JavaScript can also run in Firefox, it can also run in Internet Explorer, probably. It doesn't matter, that it could be running on, again, different JavaScript engine, different web browser. Web browser could be running on a different operating system, different types of keyboards, different CPU architectures, and just different straight hardware, and it'll still work. So because the implementation detail of each layer is abstracted from the one above it, you don't care how it actually works. Networking is another place where we do abstraction layers, but shifting gears for a moment, let's talk about network protocols. So can anyone list any networking protocols they may have heard of?
Can.
Yeah, I'm going to start writing. That's none-n. You ever used a website?
Is it like TCP?
Sorry?
Is it like TCP?
There's TCP. I was thinking HTTP.
Okay, cool. Ethernet?
Is Ethernet. I mean, like, you could even count like USB, right? Networking doesn't strictly have to mean internet loading websites.
So does HDMI count then?
Yeah, we can put HDMI in there. Right? Okay. So let's figure out like how these sort of piece together. Because like, for example, yeah, when you're accessing a website, you could be using HTTP or HTTPS. Really, HTTPS is HTTP with other things, right? So they fit together in different ways. Those all run on top of TCP. UDP is an alternative to TCP, etc. So how does this actually fit together? So there's actually a rather formal model used to describe how, like, the different responsibilities of different protocols used in complex communication systems, like communication over the internet for the majority of these. And yeah, it divides the functional requirements of a system like this into different abstraction layers, specifically 7 different abstraction layers. So yeah, the idea is you have a protocol per layer that implements it, describing exactly what it needs to do. So lowest layer, layer 1 is, I'm just going to write out the name. So physical layer. So the physical layer is literally the exact physical requirements for communication. So that's like, for example, for Ethernet, that says like the exact connector you need, the ratings of the cable, what voltages are used, what pin corresponds to what piece of functionality, etc. So that's like actual physical layer characteristics. The idea there is a physical layer protocol tells you how to, like if you have a bunch of just raw bits that need to be sent, how do you actually send that? So again, for something like Ethernet, that would be like, how do you turn that into digital on and off? For something like Bluetooth or Wi-Fi, how do you turn that into different frequencies? How do you modulate that like across different channels? Because wireless protocols have different channels so that different devices don't interfere with each other and so forth. So that's what the physical layer does. Next layer up is called data link layer. So that's about how you actually manage communication between 2 directly connected things. So yeah, 2 things that are plugged into each other or wirelessly communicating directly with each other. We're not talking about like getting across the world here, right? So generally this includes like, how do I just turn raw bits into like physical signals? This says, okay, how do I actually turn that into like, say, frames? Packet framing is a fairly key requirement of this. So we're not just talking about a raw stream of bits anymore. We're talking about like discrete messages between the 2 nodes. Layer 3 is network layer. Okay, so the network layer is where we actually get into interesting, useful applications. That would be how you get data from one point to another, or from one node to another is how it's formally described, that are not directly connected to each other, or not necessarily directly connected to each other. And there could be, depending on the system, there could be multiple possible routes of getting there. Like, there could be, so yeah, it may need to make some routing decisions. It probably needs to make some routing decisions anyway, because the very first device might not have a map of your entire network, especially if it's something as big as the internet. Maybe if there's only one route, it still needs to figure out what that route is, right? And a lot of the times, all right, for everything that we described so far, in a lot of cases, it's not guaranteed to be reliable. So if you send a packet over a network, it's not guaranteed to get to the other end. It's not guaranteed to get to the other end uncorrupted. So there's often, so some of the higher level protocols or layers that we'll get to, one of the responsibilities is to do things like error correction. So that's often implemented in the layer 4, which is the transport layer. So transport layer It does things like multiplexing. So network layer can get you a piece of data from one computer to another, or from one device to another. Transport layer says, okay, I'm gonna then, like, when I receive a packet, I'm gonna be able to figure out like what piece of software, what application, or what purpose on this device is that supposed to be for. So, for example, you may have a server. Let's say, for example, the server running our team website has an HTTP and HTTPS server. Those are two different ports as far as the transport layer protocol is concerned. It also has SSH, which is how I can connect to it and update the website. And so the thing that decides what application handles incoming communication and encodes what application outgoing communication is going to is all done in the transport layer. It'll also often have things like error detection, segmentation, which means if you're sending a lot of data, it can split it up into multiple packets and reassemble it at the other end. You have acknowledgement, which means that you send data and then you get a message back, hopefully a few milliseconds later, saying, yeah, I got it. And then if you don't get, maybe if there's one packet that you just didn't get an acknowledgement for, you may send it again to make sure that actually got to the other end. Things like that. And there's layer 5, which is the session layer. When you load a web page, it'll start a session with the web server. You'll send all the information about what web page you want and any other additional information like cookies and whatnot, and then it'll send back the contents of the web page along with all the other information, and then that'll be the end of the session. How exactly you define a session can sort of depend on the context. So in the context of HTTP, it could mean just one request and response is one session, or sometimes servers will support keeping the underlying connection open for longer to save time if it needs to do another request and so forth. So you could consider that whole thing to be one session. So it depends on how you define it, but that's to do with the session. Layer 6 is presentation layer. The actual data that needs to be sent across the network isn't necessarily in like a raw binary format. So the presentation layer is generally what's responsible for taking what could be like actual like structured data and encoding it into binary format. So that can also include, for example, byte order translation. So if you're not familiar with what that is, when you have, say, a 4-bit integer, on some computers, the lowest, so 4-byte integer, so you could have, let's say, it's stored at address 0. So there'll be, so there'll be 4 bytes, right, starting at address 0. Let's say the integer is 10. You get the point that then 3 of them will be 0. On some computers, that'll be encoded as in hexadecimal as that. On other computers, it'll be encoded as that. So some put the most significant byte first, some put the least significant byte first. There's different reasonings for both, but generally if you're sending a binary encoded integer over the network, you want to you want them to agree ahead of time on what order. And if it's different than the order that's built into the architecture of the computer you're running on, then the presentation layer is what's responsible for translating that, so flipping the order around, right? It could also include things like encryption and compression and things like that. Then again, just like taking data and turning it into the actual like raw data that then gets sent over here. Because each of these basically just gets like a raw hunk of bytes from the layer above it and sends it. This is where we're actually talking about structured data, and then that brings us to the highest layer, layer 7, which is the application layer, which is the actual application-specific protocol. So that would be like, if we're talking about like HTTP, that would often fit in there. So actually, let's talk about, for example, if we're loading a secure website, like let's say if you go to like google.ca, it'll load over HTTPS. How does that actually work in terms of this model, the OSI model? So first of all, loading a website says HTTP is the application layer protocol. You can write that over here. Presentation layer. We mentioned that encryption can sort of fit in there, right? So if we're talking about this is HTTPS, then TLS, which is the encryption system used by HTTPS, can go into presentation layer. And that also implements some session layer stuff. Then there's TCP, which generally fits in the transport layer, but also implements some session things. So that manages a connection, so it has opening a connection and closing a connection, but the entire rest of its functionality describes what's implements what's described in the transport layer of the OSI model. So like error correction, making sure packets get to the other end, and so forth. Networking layer, or network layer, is IP, the internet protocol. Data link layer, that can change. You could be, like let's say you're loading it on your phone. It's probably going over Wi-Fi, right, to the nearest access point, which probably then has an Ethernet cable connecting it to some other switch, which has another Ethernet cable and so forth. And then there's probably a fiber line somewhere along the line. So all of those describe both a data link layer and a physical layer of the protocol hierarchy. In a lot of systems, there will be a single protocol that describes both of these, because often this is not particularly useful without that, and vice versa. So this could be Ethernet. Or, for example, if you didn't have Wi-Fi turned on, it could be over mobile broadband. Or if you were on your computer, but you were tethered to your phone, you have then Ethernet emulation over USB. So USB is now fitting somewhere in here. So, or you could be tethered over Bluetooth. It's another different protocol that can fit in here. But so you can see how when you split it into a model like this, then you can sort of patch things on top of each other, like how you can communicate over Ethernet or Wi-Fi or Bluetooth or USB and still get the exact same rest of the protocol stack. Briefly, so we figured out where these all fit in. What about the other ones that were brought up? So CAN describes a physical layer and a data link layer. CAN is a communication bus used in things like cars and other embedded systems. Depending on, you can't really say it describes a network layer, because even though you can have multiple things on the same bus, they're all directly connected to each other. But you can build higher level protocols on top of CAN, because again, all this does, like all Ethernet knows how to do is just send broad hunks of bytes, and then the rest is all built up on top of that. So you could build, for example, IP on CAN if you wanted to. So that is 1/2. TCP was 4 and a bit of 5. HTTP fits in layer 7. HTTPS, I guess kind of 5, 6, 7 if you include TLS as part of it. Ethernet is 1 and 2. What about UDP? Anyone heard of UDP? So use the datagram protocol. So TCP is the transport layer protocol you use on the internet protocol suite if you want connections. If you just need something that sends a single datagram with no response, no guarantee that it got there, whatever, you use UDP. So that's a transport layer protocol. That's most often used, for example, streaming audio and things like that, because if it drops, you don't care if it drops one packet, because you get a very short amount of time, like a very short amount of audio that's lost. But you don't want to spend all the network resources to make sure that every single bit gets there without like corruption or anything, because it's audio. If it gets a little bit corrupted, or if it gets if like 1 or 2 packets get dropped every second, the user may notice, but probably won't care. But you'd rather not use up more network resources. So that's UDP. HDMI, harder one. Definitely specifies layer 1, definitely specifies layer 2. No such thing as layer 3 for it. I don't know enough about it to say how it does that, but I say definitely not layer 3 because you can't like make a network of things with HDMI. Although actually, what if I throw in DisplayPort? You can daisy chain with DisplayPort. So DisplayPort does implement a layer 3 protocol as well as a layer 1 and a layer 2. And one more thing wanted to fit in the discussion about the OSI model overall and all these is addressing. So in order to send data from one thing to another, especially when we're talking network layer and up where there's like many possible recipients, you often want basically everything needs to have a unique address, right? That's often the case for the lower level protocol, or for like layer 1, layer 2 protocols as well. Because many layer 1 and layer 2 protocols, you can have multiple, even though this is supposed to be direct connections between things, it can be set up such that there's multiple things on that direct connection. So that's not really the case for Ethernet, but is the case for like Bluetooth, Wi-Fi, etc. You need like just Wi-Fi. I mean, it's literally everything within like a certain several meters of your device is basically directly connected to it, whether or not you're actually sending data or not, right? So you need to be able to identify which device you're sending a frame to. CAN is another example because CAN it's a bus that you can just plug multiple devices onto. So you need to be able to identify which device you're sending data to and so forth. So yeah, we need addresses. When you're working generally with things in the Internet Protocol Suite, like all those, there's 2 types of addresses that every device has. It has an IP address, and has a MAC address. MAC is, don't know what it stands for off the top of my head, has absolutely nothing to do with Apple. MAC addresses, MAC is a layer that's built into Ethernet, Wi-Fi, Bluetooth, USB, and so forth that allows you to identify the device that it's connected to. So everything has a unique IP address and a unique MAC address. When you're like sending data at any of these levels, you're identified by the IP address, and then there's something called the address resolution protocol, which figures out how an IP address maps to a MAC address, so it knows what to tell the data link layer in terms of how to send it to that device.